In this lesson, we're going to do three things. First, we're going to walk through the process of actually solving the Schrodinger equation mathematically for a specific case called the infinite square well. Then we're going to talk about the time dependence of wave functions even in equilibrium. And lastly, we'll talk about the orbital model of the hydrogen atom. The Schrodinger equation at face value is not a terribly complicated equation. It only depends on two things: the mass of the particle and the potential in which the particle exists, which essentially represents the forces acting on the particle. Inputting just these two pieces of information into the Schrodinger equation and making use of the Born rule allows us to determine every single possible wave function that can describe this particle, as well as the energy corresponding to each wave function. The Schrodinger equation tells us the energy eigenstates of a system. It allows us to write down a wave function that describes a definite energy state. And because of the linear properties of the Schrodinger equation, combinations of energy eigenstates are also allowed states of the system. Such a combined state is not an energy eigenstate because each component of this overall wave function corresponds to a different energy, and an energy measurement on such a state would, according to the Copenhagen interpretation, randomly select out the energies corresponding to one of these individual eigenstates that make it up according to their various probability amplitudes. But despite the fact that very little actually goes into this equation, it can be very challenging to solve in practice. In particular, if the function v of x is even remotely complicated, then this equation can be anywhere from very challenging or impossible to solve exactly. There are two special cases of the potential function v of x that actually result in an easy solution. The first is when v of x is equal to infinity. In that case, then any finite amount of energy E is going to be completely irrelevant, in which case we can just remove this term from the Schrodinger equation entirely. And here we can see that if the wave function is not equal to 0, then the curvature of the wave function must be infinite because v is infinite. But as we already discussed, anytime E is less than v, which it has to be in this case, the wave function needs to be asymptoting towards the x-axis. It needs to go to 0 in order for a wave function to be normalizable. For example, we can use curvature to analyze this particular wave function that I've drawn here, and we can see that to the left of the inflection point here, v must be greater than E because the wave function itself is positive, the curvature is manifestly positive, and therefore E minus v has to be a negative number to cancel out the overall negative sign in the equation. But if the potential in this region were infinite, then the curvature is infinite, and that means that the slope will vary infinitely fast. Rather than slowly asymptoting towards 0, it would infinitely curve upwards. Such a wave function could never be normalized, and so in any region where v of x is equal to infinity, the wave function has to be equal to 0 exactly. The second scenario is when v of x is a constant value. In this case, we can clean up the Schrodinger equation a little bit. Specifically, we can factor out the wave function from the right-hand side, and since E and V are both constants, we can represent the quantity 2m times E minus V over h bar squared as a single constant value. This implies that the curvature of the wave function has to be equal to the negative of a constant value times the initial wave function. And you should already know from calculus that this describes the sine and cosine functions. Sine and cosine are the functions whose second derivatives are proportional to the negative of themselves. That means that the solutions to this equation are simply a combination of sine and cosine functions with appropriate arguments so that the derivative gives us this factor of a, as well as coefficients c1 and c2, which can be different from each other, and whose values depend on the actual potential as well as on the Born rule. Also note that the square root of a can be expressed as 2 pi over the wavelength of these trig functions. This quantity shows up so often in, not just here, but in any study of waves in general, and so the quantity 2 pi over lambda, or in this case the square root of a, is often written as k, which is referred to as the wave number. Either of these two examples alone is boring. If v of x is infinite everywhere, then our wave function has to be 0 everywhere, which means that we can't have a particle. It doesn't make sense. But if v of x is equal to a constant value everywhere, then our wave function is just an oscillating sinusoidal function everywhere. And such a wave function can never be normalized. It's not possible to make this satisfy the Born rule. However, it is possible, it turns out, to combine different solutions to the Schrodinger equations in this context with different values of energy. If you combine lots of different energy solutions to this equation together, so trig functions with different wavelengths and frequencies, it's actually possible to make a wavelength, a wave function that is contained. And we call this kind of thing a wave packet. This represents the free particle solution to the Schrodinger equation. We call it a free particle because if the potential is constant, it means there are no forces acting on the particle. And if there are no forces acting on the particle, it's free. But we see that the blue wave function here doesn't work. It can't be normalized. It can't actually represent a physical wave function. But the red represents a combination of many blue waves with different frequencies. I'm not going to go into the math of how this works, but ultimately what we've done here is we've confined the particle to a much narrower region. The blue particle would be equally likely to be found anywhere in the entire universe. A particle described by this red wave function is most likely to be found somewhere in this region and very unlikely, for example, to be found out here because the wave function is getting smaller and smaller, even though it keeps oscillating back and forth. What this means is that a free particle cannot exist with a definite amount of energy. A free particle wave function can only be normalizable if you combine multiple energy eigenstates together. Neither of these two specific scenarios are very interesting. They're both very easy to solve, and the second one in particular does lead to some interesting conversations about the nature of free particles. But if we want to talk about a particle that's contained within some potential well, we can actually combine these two specific cases and create what we call an infinite square well. Here we have a region between x equals 0 and a, where the potential has a value of 0, a constant value of 0. And to the left of 0 and to the right of a, the potential is infinite. Right away, we can apply what we learned just a moment ago. We know that the wave function has to be 0 everywhere the potential is 0. And we also know that it has to be a combination of sine and cosine functions within any region where the potential is constant. That raises three questions. What must be the values of b, c, and k? B and c are the easiest to address because our wave function has to be continuous. It can't be multi-valued. It can't jump discontinuously from here to there, for example. And that means that b times cosine of kx plus c times sine of kx has to be equal to 0 when x is equal to 0. This is called a boundary condition. When you're solving a differential equation where one of the functions in it is defined piecewise, you have to match up all the boundaries between the different pieces of the solution. There are lots of different solutions within this region, and there's only one solution in this region, and we have to make sure that the solutions in this central region line up with the solutions on the left and on the right. And since the sine of 0 is equal to 0, and the cosine of 0 is equal to 1, that tells us that b is equal to 0. We can also apply the boundary condition at a, because the wave function has to be 0 at x equals a as well. And since we already established that b is equal to 0, we only have to worry about the sine term. Now, if this is equal to 0, one way we could make this work is by setting c equal to 0. But c is a constant. If I set this equal to 0, then my wave function becomes 0 everywhere, and I'm describing a state of a particle that doesn't exist. So that's not what we're looking for. But another way to ensure that this is 0 is to impose a restriction on the possible value of k. A is determined by our scenario, so we can't change a. That's just what we're dealing with. But k depends on the energy of our state. And in particular, to make sure that this is always equal to 0, k times a must be equal to an integer times pi. But k is related to the energy of the system and the potential, but the potential within this region is 0. We can rearrange this to solve for the energy of the system in terms of the other variables. And I've labeled the energy with the subscript n to make it clear that this n in the equation can take on any integer from 1 to infinity. So there are a lot of solutions to the Schrodinger equation for the infinite square well. One occurs when n is equal to 1. That gives us the ground state solution. N equals 2 halves the wavelength and gives us the first excited state. N equals 3 adds another half a cycle and gives us the second excited state, and so on. And last of all, we can use the Born rule to normalize our wave function to find the value of c, which, if you do it, turns out to be the square root of 2 over a. And the energy eigenstates can be written, therefore, as the square root of 2 over a times the sine of n pi x over a, corresponding to the energy eigenvalues that we previously determined. This is the simplest bound state that we can describe. It describes a particle that is completely free to move between some region between x equals 0 and x equals a, and it has zero freedom at all to exist either anywhere outside of that region. This is the simplest possible bound state. It describes a particle that is completely free to move along a single dimension between some region between 0 and a, and that cannot exist outside of that region. And while infinite potential is not really a physically realistic thing, very, very, very large potentials can be approximated well as infinite. And the difference is that in the real case, there would be a very slight possibility of finding the particle outside of the well itself, but it would be very, very, very small, potentially negligibly small. It's actually possible to build systems that are kind of like this even. For example, a tiny little stretch of very narrow wire can be treated as one-dimensional, and the particle, an electron, for example, would be very unlikely to be able to jump off either end of the wire. Other examples include thin strips of graphene or carbon nanotubes, or I'm sure there are lots of other variations that I'm not aware of. But despite the fact that we're talking about a really simple one-dimensional model, the general conclusions from this apply very broadly to almost any kind of bound state. The measurable energies are quantized. Only certain energies can exist. This is just like the hydrogen atom. And the higher the energy state, the closer and closer to the classical expectation the probability density becomes. But this isn't the whole story. These represent the time-independent wave functions, which means we've removed all time dependence from them. These represent what the wave function looks like at a single moment in time. And it turns out that even in equilibrium states, wave functions are not so static. Adding in the time dependence is actually pretty easy, although I'm not going to prove that this is how it works. But basically, if you have an energy eigenstate, to add in the time dependence, you just multiply it by e to the I omega t, where omega is the angular frequency, and if you recall from a couple lessons ago, that can be expressed as the energy of the state divided by h bar. Or maybe it'll be more recognizable if you think about this as E equals hf, which is the same thing. Omega and h bar simply have extra factors of 2 pi that cancel each other out. Now I'm going to add in subscripts of n because E, the energy, depends on the state, and therefore the frequency also depends on the state. For example, the first two energy states of the infinite square well that we just solved would look like this. And since the energy is proportional to n squared in the case of the infinite square well, E2 is equal to 2 squared, or 4, times E1. That means the second energy level has 4 times the time frequency as the ground state. What does this all mean? Well, first of all, note that the time-dependent wave function has the same magnitude as the time-independent wave function, because e to the I omega t times its own complex conjugate is equal to 1. So when we take the magnitude squared of the time-dependent wave function, we get the same probability density. Consider, for example, when t is equal to 0. E to the 0 is 1, and so at t equals 0, our wave function is the same as it was before we added this time dependence. But as time progresses, when E1t over h bar becomes pi over 2, e to the I pi over 2 is equal to I, and now our wave function becomes the same magnitude as it was before, but now it's completely imaginary. And so the wave function oscillates in time between being real valued and imaginary valued. And that means at some points in time, most of the time, it has a real and an imaginary component. And the higher energy level you have, the higher the rate at which it oscillates back and forth. You can visualize it like this. In this animation, you can think of the blue part of these functions as being the real component and the red as being the imaginary component. And as you can see, they're oscillating back and forth. And when the blue component is getting bigger, the red component is getting smaller, and so on. So the left-hand side is the wave function, including the real and complex components. The right-hand side is the probability density. And you can see that even though the real and imaginary components are oscillating back and forth, the sum of their magnitude squared is still a constant value. This is why the energy eigenstates are called stationary states, because their probability densities are stationary in time. Even though the wave function does change over time, the associated probabilities do not. You can also see, by the way, that the first excited state oscillation happens much faster than the ground state. And in fact, if you time them, you'll find that the frequency here is 4 times the frequency at which these oscillate. And that's because these are actually the equations for the wave functions for the infinite square well, or something very close to it. This bottom state is different, though. First of all, you'll notice that the probability density does depend on time. And second of all, you'll notice that these blue and red curves do not look like sinusoidal in the same way that these do. They kind of undulate back and forth. And that's because this state is actually a superposition of these two states. If you add these two red curves together, you get this red curve. And if you add these two blue curves together, you get this blue curve. So this state represents a superposition, or it represents a particle in a superposition of being in the ground energy state and in the first excited energy state. In other words, if a particle is in a state of definite energy, then its probability density is stationary, it's constant over time. On the other hand, if a particle is in a superposition of energy states, then its probability density will vary or oscillate over time. One of the other videos that I've linked to goes into this in maybe a little bit more detail with a 3-dimensional visualization that might make it a little bit easier for you to follow. And last, but certainly not least, is the hydrogen atom. There's no way I can let you leave this class without at least talking about it a little bit. After all, this was one of the many motivations that we talked about that led to the development of quantum mechanics. And while the Bohr model was able to match the quantization seen in the absorption and emission spectra of hydrogen pretty well, it was insufficient, imprecise, as well as, in some cases, incorrect. And one of the greatest successes of the Schrodinger equation, and the reason why it was accepted so quickly and so uniformly, is that just by plugging in the electric potential between two opposite elementary charges, the Schrodinger equation outputs 3-dimensional wave functions with corresponding probability densities that are consistent with essentially all of our measurements of the hydrogen atom. And what these wave functions lack can be added in by taking into account special relativity, although we are not going to do that here because relativistic quantum mechanics is just a little bit more challenging. This equation might look a little bit unfamiliar. This upside-down triangle is basically a 3-dimensional derivative, and now I've made my wave functions of a vector, a 3-dimensional vector r. But otherwise, it really means the same thing. And this, of course, is the electric potential between two elementary charges with opposite sign. Now, unfortunately, actually solving this equation is very laborious and just a little bit harder than, for example, the infinite square well. And we're done. This chart includes the wave functions for the first 3 energy levels of the hydrogen atom. You might be thinking, that's more than 3 equations. And that's because for the hydrogen atom, it turns out that there are multiple states corresponding to the same energy above n equals 1, above the ground state. There are different amounts of angular momentum that a state can have within a given amount of energy. And that's what these S's and P's and the corresponding zeros and ones and twos and stuff here are basically representing. They are representing different configurations of the electron, but the number out front actually represents the total energy of the state. Also, Z for hydrogen is 1. These equations are often referred to as hydrogen-like wave functions. If you plug in Z with a bigger number, it would describe a hydrogen atom that has a greater number of protons in the middle. And it turns out that this is not a terrible approximation for hydrogen-like atoms, other alkali metals in the first column of the periodic table. It doesn't get things quite right. The effects of the other electrons do matter, but it's a rough approximation that's sometimes good enough. Now, the general solution for the wave functions of the hydrogen atom can actually be written down in a single, relatively concise form. You'll notice there are 3 subscripts here, and that's because the wave function depends on n, the energy level, L, the orbital angular momentum of the electron, associated kind of like with a planet's angular momentum as it orbits around its sun, and m, the intrinsic angular momentum of the electron, which is what we call spin. There are some constants in here, like the reduced Bohr constant. You'll also notice rho, which is kind of like a beat-up version of r. It's a function of r. It depends on n and the reduced Bohr constant, but it's basically r. This capital L with the crazy superscript and subscript represents Laguerre polynomials. Laguerre polynomials form a complete orthonormal basis for all polynomials, so you can construct any polynomial based on some combination of the Laguerre polynomials. And then this YLM thing is called a spherical harmonic, which is essentially a three-dimensional spherical version of sine and cosine. But being three-dimensional, they're a bit more complex. And it depends on the 2 angles in spherical coordinates, theta and phi. This one single equation represents the energy levels, the wave functions of the electron of a hydrogen atom for any energy level, any angular momentum, any orientation of spin. But I know what everything in this equation means, and I can't use this to help me visualize what's going on. I can't even use these equations to help me visualize what's going on. They're too complicated, except for this one. This one's easy. This stuff is just a constant, and then we have an exponential that decreases as r increases. But other than the 1s, the ground state of the electron, these equations are quite challenging to visualize. So this is why we have diagrams and other useful tools. If you've seen the hydrogen orbitals, you probably saw something that looked kind of like this. This diagram shows cross-sections of the orbitals from the n equals 2, 3, and n equals 4 energy states, corresponding to different values of angular momentum. Now, the hydrogen atom is three-dimensional. So the wave function is three-dimensional. These images are cross-sections of a slice cutting straight through the middle of the hydrogen atom. We can highlight some patterns. For example, for all 3 of these energy levels, and it would also be true for the n equals 1 ground state as well, where they have no angular momentum. That means the middle number is equal to 0. There's 1 there, there's 1 for the 3rd energy state, and 1 for the 4th energy state over here. First of all, these have no angular momentum. These electrons truly cannot be said to be orbiting their nucleus, which is how we often think of atoms. Orbit implies moving around something in a circle. That means it must have angular momentum. But in quantum mechanics, our electron can persist around a positively charged nucleus without actually having any angular momentum. It really isn't orbiting. It just kind of exists in this wave function cloud state. So our classical models of the atom really don't get it right. Moreover, these states with no angular momentum all exhibit spherical symmetry. All they depend on is how far away we are from the radius. Now, in the n=2 state, we can see that it's brightest at the center, which means that's where the particle has the highest probability density. And then it gets dimmer and dimmer as we go farther away. But you'll also notice there's a little spherical shell over here. Again, this is a cross section, so we see a ring, but it really is three-dimensional. And what that means is that there is a node, like a standing wave node right here, where the electrons will never be found in the zero angular momentum first excited state of our atom. And in the third excited state, there are 2 nodes. And in the fourth excited state, there are 3 nodes. Once we start adding in angular momentum, the patterns start becoming more and more complicated. And they clearly start to depend not just on distance from the center of the atom, but also on direction. For example, in this particular state, the electron has 0 probability of being found in this sort of central region around the nucleus, but it is likely to be found in this vertically oriented region. And this is the opposite. And in the n=3 state, again, it's similar symmetries, but more nodes. The wave function oscillates more times before petering out to 0. Another interesting thing is that if you look at this wave function as r approaches infinity, technically never reaches 0, other than the nodes along the way. But as r approaches infinity, the wave function just gets smaller and smaller, exponentially smaller, so it gets smaller very fast. But technically speaking, there is some chance of finding an electron very, 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 very far away from its atom. The probability density is extraordinarily small if you're this far away from this particular atom, but it's not 0. In practice, the probability of finding an electron even like 1 meter away from its nucleus is astronomically small. It's possible that such a thing has happened sometime during the lifetime of the universe, somewhere in the universe, but probably not. I should also emphasize, I should have done this earlier, that these are actually not the hydrogen wave function. These are the hydrogen wave function probability density plots, right? So these represent the actual probability distributions. The brighter the spot, the more like yellow it is, the more likely the particle is to be found in that region. The more purple or black, the less likely the particle is to be found in that region. And remember that electrons can exist in a superposition of any combination of these. So while these density patterns might look complicated on their own, we can make it even more complicated because our electron can be a combination of any or all of the above. Also, this just describes hydrogen, the simplest atom in the universe. The moment you add in a third charge, a second electron, in addition to the first electron as well as the nucleus, things get extraordinarily complicated. The electric potential between 2 charges is quite simple. The electric potential between 3 charges is much more complex. And in fact, the 3-body problem, the dynamics, even in classical mechanics, of 3 interacting objects, is impossible to solve analytically. And that problem is only exacerbated in quantum mechanics. So we can't repeat this process even for the helium atom. Here we have a nice closed form equation that gives us the wave functions of the hydrogen atom. But if you try to do this for the helium atom, you will not get this far. It's not actually possible to solve and get a nice equation. Now we can use approximation methods to get an equation that's close, and we can use numerical methods to get numbers that are very close, but we can't write down the exact wave function for a helium atom because it's too complicated. And to see why it's even worse in quantum mechanics than it is in classical mechanics, the potential between charges depends on where the charges are. Well, the nucleus is very well contained right in the center. Technically, the nucleus is also described by a wave function, but it's so tiny, it's almost guaranteed always to be found right in the center of the atom that we can just treat it like a particle with an exact position, and it's almost exactly correct. On the other hand, if we consider, for example, this as the probability density for the first electron in an atom, how do you write down the potential between this electron and another electron. We don't know where this electron is. Its position is represented by a probability distribution. And so the potential between this electron and another electron is complicated because this electron doesn't have a position. Its position essentially is smeared out. It might seem like a lost cause, but we're actually pretty good at using approximation methods and numerical methods with computers to get pretty close to the wave functions for more complicated atoms than hydrogen. And lastly, you may have also seen orbitals represented something like this. These are three-dimensional representations instead of cross-sections like before, but they're also solid colors. The surfaces of these shapes represent surfaces of equal probability density. Typically, either 95% or 99% are used to represent these, which means, for example, there would be, let's say these represent 95% probabilities. It means there is a 95% chance that the particle is contained within this region. Or in this slightly more complicated example, there's a 95% chance that the particle is contained within these regions. And the shapes are determined such that the value of the wave function is equal along all of these points. The different colors are used to represent the sign of the wave function, whether the wave function is positive or negative. This is important because if we superimpose any two of these states on top of each other, that will affect the interference patterns that arise. You might also encounter diagrams that are similar to this, but with smoothly changing colors across like the whole rainbow, and that's usually used to represent the full complex phase. So it'll switch colors between real and imaginary and everything in between. And of course, these wave functions are not static. They also have time dependence, just like in the case of the infinite square well. And so the phase is actually changing. So this is like a snapshot of the phase of the wave function in one moment in time. And if we were to play it forward, the colors would be changing corresponding to the rotation in the complex plane of the wave function. I hope now you have a greater understanding and appreciation for what the orbital model of the atom really means and where it comes from. Electrons don't actually orbit their nuclei in any meaningful sense of the word. They're described by a wave function which determines where the electrons are likely to be, but the electrons are not actually zipping around and we just don't know where they are. They literally exist in a state of superposition of positions until we actually go and look for it. We've actually been able to experimentally measure the shape of a lot of the orbitals of atoms, and we can do this by bombarding an atom with electrons or other particles like photons, and make a measurement of where we found the electron. And if we do this many, many, many times for a bunch of atoms that exist in the same state, we can count up where we found the electrons, and we can start to piece together an image of where the electrons in that particular state are likely to be found.